Hi everyone, welcome back. So what I have showing here, it says closed form ROC rules, stands for rate of change. This is listed in Canvas in Module 2 as derivative rules. That's what these are. These tell you the rate of change of a variety of sorts of functions. This uses our third different notation, the R with the subscript, to indicate exact rate of change. So you can see the rules we were talking about last lesson are over here. The rate of change of a constant is 0. Power function, that's power rule. This is the shortcut for if you're dealing with a square root, 1/2 power, although power rule works also. These two we talked about the last day of class. The derivative of an exponential function with base of exponent as the constant a is a to the x times a constant. That constant turns out to be, through proofs that we'll show later, the natural log of the base. The natural log of e is 1, so just as a, remember this, if it's e to the x, e being Euler's number 2.718, etc., the derivative of e to the x is e to the x. Easy to remember, but just keep in mind what that means. It's not, the function is its own derivative, they just have the same they have the same rule as one another. Now, two that we didn't talk about, that it's a basic sort of function. Logarithms are inverses of exponential functions. And again, we'll get into some of the proofs of these later on. But a logarithm with a base of b, its derivative rule is that we have 1 over x, the input to the logarithm, times the natural log of b, also in the denominator where the x is. For natural log, which means the same as log base e of x, the derivative is 1 over x times the natural log of e, which is 1, so it's just written 1 over x. So again, this is a special case of this logarithm rule, just as e to the x's derivative rule is a special case of this a to the x. E is special number, which is very nice to use in calculus. It's kind of unwieldy if you're trying to make tables of values by hand in an algebra course, but luckily that's not what we're doing. So the other two columns I've got here, I've got trig functions. I just want to kind of read through these and point out some things. So usually you learn these in two chunks, like sine, cosine, and tangent, and then they're reciprocal functions, which are cosecant, secant, and cotangent in that order. But the reason they're in this order is because of the ways that the derivatives match up. So I do want to talk about this a little bit, but sine of x, its derivative function is cosine of x, and cosine of x, its derivative function is the opposite of sine of x, or -1 times sine of x. So just thinking visually about this, let me pull up a GC window. We'll deal with that later. If I were graphing y equals sine of x, looks like this. And so I can see near the origin, this is going uphill, just a little bit to the left and a little bit to the right. It reaches a peak around, well, I know it's at pi over 2, but a little bit past, or right around 1.5, 1.57, whatever, and then decreases for a while, then increases, and it repeats over and over again. So thinking of what its derivative function, what qualities its derivative function should have. Its derivative function should be approximately 0 around these peaks and valleys. Should be positive and negative otherwise, alternating back and forth. So it should make sense that it's another cyclical function with the same period, 2 pi in the case of sine of x. And y equals cosine of x meets that specification. Now, I'm going to graph these, let's see, y prime. So the prime in GC, remember, doesn't mean derivative. It splits your graph window, so you have two graphs, left and right. And let's see, cosine of x prime. Now, just comparing these. So sine function here, as I said, it's increasing and then decreasing and then increasing if I start from the origin. So this has a positive value, this cosine function does, and then it reaches a negative value just past 1.5, where it passes through 0 right around pi equals, or pi over 2, 1.57-ish. So that should make sense. And then in terms of this. So this cosine reaches this minimum just past 3. So you can maybe guess, oh yeah, that's at pi. So it reaches this minimum, which what that would mean, this is a negative number, the most negative, thinking about what's going on at pi here, just past 3. This is at this intercept here, actually. That's the most negative slope, if you want to think of that, or this is decreasing most rapidly right around this part, whereas it's increasing most rapidly at these other intercepts where it's on the way up. And this is the peak of the cosine function, its highest value, so rate of change of 1 at the origin, rate of change of -1 at x equals pi, and so forth. And it repeats over and over. Similarly, if I were looking at, let's see, let me just switch these. I'm going to y equals cosine of x, and on the right, I want to graph its rate of change function, which according to that sheet we were just looking at was negative sine of x. So if I'm thinking of this as the main graph, and what would its rate of change look like? All right, so rate of change around 0 at the peaks and valleys. So at 0, at pi, at 2 pi, and so forth, the rate of change of this purple graph should be 0, meaning if I'm graphing the rate of change, its dependent quantity should have a value of 0 at 0, at pi, at 2 pi, and so forth. So that, again, cyclical, it should make sense that it's got to be another periodic function with a period of 2 pi. Now, as for the negative, think about this cosine function. This cosine function is decreasing from 0 to pi. So when I'm looking at its rate of change, the rate of change of this should be something negative, all the way from 0 to pi. Well, with values of 0 and at pi, but negative in between. So therefore it needs to go down and back up between these two zeros, which is exactly the reverse of what the sine function does. Sine function goes between 0 and pi, goes up and back down. So just in terms of, does this make sense that these functions are kind of one another's derivatives? I hope that makes sense. But let's take a look at what those rules were again. So sine's derivative is cosine, cosine's is negative sine. Tangent and cotangent have the same sort of relationship with one another. Now they aren't one another's derivatives, but, and we'll prove this in just a moment, tangent's derivative is secant squared. Cotangent's derivative is cosecant squared with a negative sign. So now these are all of x. If there's something other than just an x there, that involves a rule we'll talk about next lesson, chain rule. But sine of x's derivative is cosine of x, and cosine's is negative sine. So sine and cosine, like the same word with a co in front of it, the co one has a negative in front of its derivative function, just in terms of ways to remember all these bizarre looking things. Tangent and cotangent have similar derivatives to one another. This one's secant squared. This has a negative in front of it and a co in front of it. So tangent is secant squared, cotangent is negative cosecant squared. And then going on to secant and cosecant, the other co-functions. Secant's derivative is secant times tangent. Again, we can prove this with quotient rule. Cosecant's derivative, opposite sort of word, it's got a co on it instead of not, has, well, the same functions but with co on them. Instead of secant, it's got cosecant. Instead of tangent, it's got cotangent, and it has that negative sign. So there's patterns between these. So if you can remember sine's derivative, tangent's derivative, and secant's derivative, the others are just, well, add or get rid of a co and add a negative sign. So we'll talk about the arc-trig functions later, and these are also something we'll prove later in the course. But these are similar in that, like, arc sine and arc cosine, which, by the way, there's two different notations for these, and I think it's mentioned up here. Yeah. So this is written as sine to the -1 of x. That's like inverse of sine. That's not reciprocal of sine. So this isn't the same as cosecant at all. This is, the input is the decimal between -1 and +1, and the output is an angle measurement. But thinking about this. So this is one notation. Another notation is arcsine of x. For the purposes, if you're writing in GC, GC doesn't like all those letters. In GC you use a sine, and similarly a cos, a cos, a tan to indicate these arc functions. So in any case, those are those. The difference in the derivatives between inverse sine and inverse cosines, or arc sine and arc cosines derivatives, is just a negative. The difference between tangent and cotangents arc function derivatives is, again, just a negative. And similar between arc secant and arc cosecant, the difference between their derivatives is just a negative. So all the functions with the co on them, cosine, cotangent, cosecant, have these negatives in front of them, just like the non-arc functions, the regular trig functions with co. So just in terms of, although we haven't proven these yet, ways to remember these bizarre looking rules that can kind of cut the number of things you have to focus on down considerably, because they do look a bit of a mess. But once you see the patterns to them, it's easier to just memorize these. It's kind of like memorizing your sevens table in multiplication. It's a little bit annoying. There's lots of, they all end in different numbers, and it's not as easy to just know off the top of your head. But once you've seen them enough, you can just, again, get used to them and recall them. This is not the main focus of calculus. Like I said, this is just the memorizing stuff. You're welcome in reality in later life to look them up whenever you feel like it, but the more that you know off the top of your head, the easier just getting through some basics will be for you. So let's take a look at, let's see, where's my other GC window? Some other sorts of functions. So I said we'd prove the derivative of tangent was secant squared, specifically as tangent of x being secant squared of x. That's actually what this h function is about. So we'll get to that in a minute. I just want to do these other quick ones first. So just in terms of finding derivatives of things, let me write this in something brighter. So f here, I can see I've got two terms. One has a coefficient of 5, or a constant multiple of 5 on an exponential function. Make sure you realize this is not the same as 10 to the x power, because this 5 doesn't have an exponent of x and the 2 does. So those two pieces can't be combined. 7 times sine of x, that's just a constant multiple on a sine function. So if I want to find f prime of x, I've got a coefficient of 5, and I need to find the derivative of 2 to the x. Well, it's 2 to the x times a natural log of 2. And you're welcome to write this with parentheses like it was originally, or a dot. I tend to typically not write dots for multiplication just because it's misleading. When you have multiple terms, that dot doesn't indicate that you have to do the distributive property, whereas parentheses do. So typically I'll write this sometimes just for little short things where there isn't any distributing. I'll write a dot, but just be careful with that. Second term, the derivative of 7 sine of x is 7 times as much as the derivative of regular sine of x, which is cosine of x. Now look carefully at this function g of x, 4x cubed natural log of x. I've got a power function and a logarithm function that are multiplied together, which means if I want to find the derivative of this, it's going to require product rule. So just keep that in mind. Either of these two pieces are easy enough to find the derivative of on their own, but since there isn't a simple plus or minus in the middle, I don't just get to slap them back together. I need to find the derivatives of the two separately and piece them together with product rule. Now, I'm going to do that this way this time. So the derivative of 4x cubed would be 4 times 3, x to 1 lower a power, times the original natural log of x, plus, other way around, the original 4x cubed times the derivative of natural log of x. So this is 1 over x, and there's that dot again. So there's not really any distributing to do here. In terms of writing stuff out, you are welcome to just leave it like this. Now, I do want to point out those two can be simplified. It's just the same as 4x squared. But again, don't spend your time doing algebra, please. Now, as for this h of x, if you remember that tangent of x, trig identity-wise, is the same as sine of x over cosine of x. If I can find the derivative of h of x here, it should come out to be what we just saw on the previous page. It should come out to be that the derivative of this quotient is the same as the derivative of tangent of x, which we saw was secant squared of x. So I'm going to jot that down here and see if we can't get that to appear as our answer. Now, this will involve using some algebra, trig identities specifically, but if I think about how do I find the derivative of this, since it's a division problem, I'm going to use quotient rule. And then, so we're going to actually prove that it comes out to be the same as tangent of x's derivative is listed as being. So I know that the derivative of sine of x is cosine of x, and I know that the derivative of cosine of x is -1 times sine of x. So just jotting down those derivatives for myself. If I want to find h prime of x just from that form, I'll say, all right, the derivative of the numerator comes first. Cosine of x times the original denominator, cosine of x, minus, other way around, the derivative of the denominator, negative sine of x, times the original numerator, which is sine of x. So I'm going to have minus negative sine of x times sine of x. So that's our numerator of quotient rule, and the denominator is the original denominator squared. So just a note about trig functions, cosine of x squared, I can of course write this way. A standard notation for that, another way that that's often written, is with the squared in the middle of it. The reason being, here, this means the same as cosine of x squared. The reason that this is sometimes used is A, it eliminates a level of parentheses, but B, instead of putting the squared at the end without those extra parentheses, this is preferred so that it's not accidentally interpreted as being that the x is squared. It's that the result of cosine is squared, not the input to the cosine is squared. So you can use either one of these, but those are not the same as cosine of x squared. So that's why I wrote the extra parentheses here to make it look like how quotient rule did, but this is more often how it's written. However, you're not able to type that into any sort of calculators because, well, after cosine, it wants an argument. It doesn't want exponents. So realize if you're typing into GC, you'd need to write this, which is, easy to remember anyway, but you'll see in books and references all the time, you'll see this notation, and I use that a lot also just out of habit. I don't want that to be a confusing point. All right, so let's get back to this h prime of x. Clearly it doesn't look like secant squared right now, but that numerator, cosine of x times cosine of x, here I'll use this fancy notation, is cosine squared of x. And then minus a negative, sine of x times sine of x, so sine squared of x. Fancy notation again. Now, if there's any trig identities that you remember at all from your life ever, the one that most people remember has to do with this numerator here. Pythagorean identity, cosine squared of something, whatever angle, plus sine squared of that same angle is equal to 1. So as long as the input to both functions is the same, cosine squared of something plus sine squared of the same something, it's always equal to 1. And 1 over cosine squared of x, since cosine is the reciprocal of secant, this is the same as secant squared of x, written as not a fraction. So the derivative of h of x here, I could write it, like if that were a mastery test question, I could write it like this, be done, that's the end of it. The reason I did some algebra, including trig substitutions here, is to prove that, well, since we know that this is actually tangent of x, if I do the algebra, I should be able to get a result that, instead of looking ugly like this, looks like the expected derivative of tangent of x, which is secant squared of x. All right, so anything else that I wanted to mention along with these? For some reason, I thought there was one other thing I wanted to say. Well, you can use the same technique that we just did with sine of x over cosine of x to create the other reciprocal functions derivative rules. If you know sine and cosine, you can recreate all of the others from that, as long as you know your trig identities. It's not necessary, though, to know all your trig identities off the top of your head, but keep them in mind. It'll make your life easier. You'll use a lot more trig in calculus 2 in terms of being able to do some additional sorts of integrating, that is, recreating the accumulation functions. There are many that are kind of hard to see, and rewriting occurs by using trig identities. All right, I'll stop at that for this short lesson and see you next time with some chain rule.